Before looking at Linux running on the MAXI030, I wanted to talk about the hardware involved. So you can see that the board isn't quite finished. I've not assembled everything, but nonetheless it's still useful for what I need to do with it at the moment. The board is a 4-layer board I designed in KiCad. So the processor utilised is a 68030 running at 40 MHz. There's also a 68882 FPU. Jumpers are provided to disable the cache and the MMU. There are two 72-pin SIMM slots, although so far I've only tested the bottom slot. A processor controllable, buzzer and LED are included just because every computer needs that hardware. A megabyte of in-system reprogrammable flash is provided in the form of two 8-bit parts. Bulk storage is provided by a 40-pin IDE header. Usually I have a combat flash attached. The only interesting thing to say about this port is it has the DMA signals wired in, although I haven't yet made any use of them. Next up, power. A barrel jack provides the input to a switching regulator. Instead of using 7805s, I'm using one of those potted regulators. The one I'm using generates 2 amps at 5 volts. Unfortunately, I got the footprint backwards. That's slightly annoying. It just means the part hangs over the edge of the board. Never mind. One of the more interesting additions is an RTL8019 AS, which provides onboard 10 meg Ethernet. There are 4 UART ports. 2 are RS232 signaling levels, but instead of using DB9s, they're on RJ45s, following the Cisco pinouts. Another port is used for the keyboard. This is a custom keyboard I built using an old Amiga 600 keyboard membrane and buttons and an AVR controller. And the 4th port is just exposed on little pin headers for attaching a USB UART. A PS2 port is provided as an alternative means of attaching a keyboard. In fact, there are 2 pairs of signals wired in, so a keyboard and a mouse can be attached at the same time using a splitter cable. One of the things I'm quite pleased with this computer about is that it has expansion capabilities. So 4 expansion slots are provided. I'm using these DIN connectors, I can never remember the number. So that provides 16 bits, 16-bit wide access and 24 bits deep, so 16 megabytes of usable register / memory space. In addition to the address and data bus, you've got the various processor signals that are wired in, so you can do interrupts on cards. There's a wait signal, bus error signal, and so on and so forth. The board also features an I2C bus. This bus can be extended into the various expansion cards via a 4-way multiplexer. And the main purpose of this is to use EEPROMs that are attached to each of the cards that could contain configuration data. But of course any I2C peripheral could be included on a card. On the board itself you have a DS1307 real-time clock and a temperature sensor for reading the board temperature. LM75A, I think. So if you haven't guessed already, the big chip in the middle is an FPGA. Specifically, it's a member of the Flex 10KE series. I won't talk in detail about how or why I chose that part now, but suffice to say the FPGA implements all of the glue logic, it generates the signals needed by the SIMM slots, so it generates the RAS and CAS, runs the state machine for those. It also implements a SIMM's multiplexer for the 12 bits of address that are on a 72-pin SIMM slot. It implements the buzzer logic to make the buzzer generate a tone at a particular frequency, generates a system reset, implements the I2C master, implements the PS2 port logic. It's also attached to the full 32 bits of address and data bus, so it can in theory become a bus master. This will be useful for reading and writing data between the IDE port and main memory, or the network card and main memory, and so on. But I haven't got anywhere with implementing any of that. The most complicated thing it does at the moment is probably the I2C master, which I implemented myself, and the interrupt routing, which is vaguely clever, but not excessively so. One other interesting angle about the FPGA is it makes the board a mixed signal board. So the bulk of the components are obviously 1980s era 5-volt parts, but the FPGA has an internal voltage of 2.5 volts and an I/O voltage of 3.3 volts. So this 3.3 volts is both driven and drives the processor, for instance. Luckily, the Flex 10KE can be driven by 5-volt signals without an inline resistor, which is one of the reasons I chose that part versus something newer. And the reason I didn't choose something older is because it wouldn't provide enough logic, and it probably wouldn't be fast enough either, because this board runs at 40 megahertz, and previous boards that I've built, including one based around a 68020, had problems with the original Flex 10K FPGAs. I'm currently sat in front of my laptop. I'm SSH to a Linux box, which is attached via two UART ports to the MAXI030. So I'm going to run up Minicom. So this is my machine code monitor. So this was mostly written to exercise the hardware on the board for my earlier 68000 based computers, but I still use it on the MAXI030 board, and in fact I even use it to start Linux, as you'll see in a minute. Briefly, the monitor is used in the traditional sense for dumping out memory, for writing to memory and registers in hardware. So there's a tone, hopefully that comes across. I'm going to turn that off before it drives me mad. There we go. There are routines to exercise some of the hardware. So I have a command for running the IDE identify command on the compact flash that's inserted. So that's the identify block. You can see it's an Inno disk Corp, whoever they are. There's the model number, 4 GB part. I can do I2C operations. There's only one I2C peripheral currently soldered to the board, which is the DS1307 real-time clock. So I'll briefly show you that. So I'm going to write out the I2C address, or sorry, the address on the I2C slave that's going to be read from, in this case, location 0. Write that to some memory on the MAXI030 board. That's not what I want. Now I send that to I2C slave address 68. So it's in that single byte. Now I'm going to read. I'm going to read 16 bytes to 2000 from slave address 68. I dump that out. That should be the time So the positioning is, this is the hour, whoops, that first byte there, so 11:42 and 9 seconds. That's roughly correct. And then you have the day of the week, 01, which is I think encoded as a Monday. 10, it's the 10th of January 2022. These are all obviously BCD values. It's nice for humans, not so good for computers. So the other thing, or rather the main thing I want to show you is using the monitor to download the Linux kernel. So I've implemented a very crude protocol that's literally running on raw Ethernet frames. There's no TCP/IP stack here. So the protocol basically says, send a file name from the MAXI030 to the Linux box, reply with a file size or 0 if that file is missing, and then enter a loop where it sends a kilobyte of the file at a time, and after receiving it, the MAXI030 sends what it got back to the Linux box, and the Linux box then checks that what the MAXI030 got is correct, and signals accordingly. And if there's an error, then it just retries that 1 kilobyte block, and it will do that indefinitely until the entire file is sent. But I don't normally have any errors. So off we go. So this, unlike the rest of the monitor, the network card handling is implemented in C. There's no C library though. There's a few string.h functions pasted in there for string length and memory copy and memory compare, and a printf implementation. So there you go, each hash on the screen is a kilobyte. I think it's about 40 seconds to send 4 megabytes. Now this kernel is essentially Linux head as of about a month ago, with my changes that I added for the MAXI030 platform as Linux terms variants of a particular architecture. So now we're going to run that kernel. So we need to give it the kernel command line. I don't have one hard coded in there, I should probably do that. So I'm using enabling the serial console support, which requires a baud rate. So this is TTY-SC 0 instead of TTY-S0, which is more common. And that's because it uses different device nodes because it's not a standard driver. And then what do you have? The root file system. I'm trying to remember that. Oops. I'm switching between US and UK keyboards all the time. Very confusing. Right, off we go. So that's the Linux kernel booting. So although the kernel is new, the userland is not very new at all. In fact, I'm currently running the Debian Sarge, which is from around 2006. That's because I've looked at running the later Debians, and it's just too slow to be usable. I need to investigate why this is, whether it's just general bloatiness in modern Linux, or whether it's something I can fix. So it's trying to look at a real-time clock now that doesn't exist. That's the driver I need to write. But we've got drivers for the serial port, obviously. Got drivers for the IDE interface, obviously. And there's also a driver for the network card, which is pretty cool. So this machine is now on my LAN. It's just getting the date from the internet there. which is a nice substitute for a real-time clock. Syslog server, inetd, there's the Telnet server is running, but also SSH and Apache 2, just for fun, and it works as well. There you go, there's the login Getty. So I'm not going to log in using Minicom, I'm going to instead switch to SSH. So if I quit out of there, and then I log out of my Linux box, so now I'm back on the laptop. I'm going to SSH. Now I need to supply this extra option here to enable SHA-1 support, because ordinarily an SSH client these days would refuse to connect to such an old server. I'm going to create a quick C file. And you can guess what I'm going to program in here. Oops. Let's give us some proper tabs. I'm using Joe here. I've never been that good at Vim. Despite trying to learn it on and off for about 20 years. And now I'm going to time compiling that. Let's see. Okay. Chan. There we go. 15 seconds. That might as well, right? There we go. Just try compiling it again. That will show the effect of the disk cache, if any. Yeah, 12 seconds. Shaved a little bit off. So I can do a quick performance test. I've got iPerf. I've got the server running on the Linux box. Yeah, 2.2 megabits. And the main limitation there is the 8-bit port, because I tried getting it working on the in 16-bit transfer mode, which is wired in, but didn't have any luck. And it could even be a solder joint problem actually, because the monitor uses 8-bit transfers. So that's the first time I've looked at using 16-bit transfers. I'll talk about the improvements I want to make in a moment. So if I become root, I can have actually I'll quickly have a look around in proc. So hardware shows it's MAXI030, shows it's got 32 megabytes. That's all passed in from the monitor using the boot info record. I don't want to do that. CPU info. There we go. Shows the BOGO MIPS, about nearly 10. Hey, 10 MIPS. The frequency is not showing up quite correctly. It's actually on a 40 megahertz crystal. Not quite sure how that works, if I'm honest. It's using a timer interrupt that's generated by the FPGA, which is pretty much spot on 100 hertz. It might be slightly out. So we've got proc. Lots of stuff in there. Never really understood what most of these mean. We've got swap as well. There we go. It's using a tiny bit of swap. So we can run top command as well. Takes up a lot of CPU power. So you can see there's 92 processors. Most of those will be Apache. because this is on the old Debian, it's running Linux threads for its threading model, which is, I suspect, why it performs better than the NPTL newer versions of Debian do. What else? We've got Fortune program, because everyone needs Fortune. Very strange. Got NetHack on here as well, but I've never really had a clue how to play it. But let's run it anyway. Yep. Maybe if I come out of there. Here we go. NetHack. Shall I pick your character's race? Role, yeah, yes please. There we go. So, NetHack. I don't even know how to move my character around, so I'm just going to have to quit this. Control C. Come on, get me out of here. Yeah, there we go. No. There we go. One day I will learn how to play that game. There we go. I've got an IRC client as well. Good old IRC2. I shall connect to Telnet. I could reminisce about this client, but I won't. Suffice to say, I first used it about 25 years ago. Come on, let me in. It does work. I don't know why it's taking a while. Oh well, it works, trust me. We have a web browser, got links. Unfortunately, it doesn't support SSL, which makes it essentially useless now. There is one non-SSL website I know, which is called Never SSL. There we go. Browsing the internet on MAXI030. It's pretty fast. There we go. Oops, resource info. No idea what any of this does. Memory info. Let's try that one. Fascinating. Search. You can do downloads. Pretty cool. Yeah, I should look from this SSL version. Yeah, it's got Telnet. Good old Telnet. So, what's next in MAXI030? Well, there's loads of things I could do. Well, it's basically about choosing the interesting / fun things, really. But I want to have a look at fixing the 16-bit or lack of 16-bit transfers on the network port. That will speed that up. I want to have a look at interrupts on the IDE port. It's not really going to make a lot of difference because I'm using compact flashes, but it would still be nice to have that. And then I want to look at doing DMA, because that would really speed things along. And as I believe I mentioned earlier in the video, which was the earlier section was recorded yesterday, the FPGA is attached to the full 32-bit address and data buses, so it should be possible on the IDE side, for instance, to be able to read and write a word, so 16 bits, in a single clock, wait states permitting on the target, if you see what I mean. So with the SIMM, a normal write would generate 3, I believe, wait states. It's still pretty quick, a lot quicker than the processor that could shovel the data. So that's DMA, and DMA on the Ethernet and possibly on the network port. That would be pretty cool. Then I want to have a look at a local graphical output instead of using the console for everything or the network, because I have a graphics card that I built and I've barely looked at it really. It's based around a Cyclone 2 FPGA, 2 megabytes of 16-bit wide fast SRAM, and obviously VGA with a proper DAC. Can't remember the part number now, but a 24-bit DAC. And I briefly played with it. In fact, there's some videos that I put on YouTube with the card being used on my earlier 68020 board. Yeah, video, that would be pretty cool. And there's a couple of ways to do it. I could either have try to figure out how to do a DOS-based, so a character-based text output like on a typical MS-DOS PC. That's one way. I have no idea how you would effectively add that functionality into the kernel. I mean, implementing the actual graphics functionality for that is pretty easy, and I've already done that on my earlier boards. But linking that to the Linux kernel is something I wouldn't have a clue about. Another approach would be to do a bitmap display in the video card, and then somehow leverage the frame buffer console in Linux to basically write data onto that bitmap display. And it should be pretty fast. I always remember when I had Linux running on my Amiga 1200, the console was pretty slow, but should be okay. If I limited the number of colours, should be pretty good. Yeah, that's where we're at. I'm pretty excited with what I've done. I hope you've found this interesting. Any questions, comments, let me know. Thank you.